Hello everyone, my name is Ayush Kumar. I am a student of third year engineering physics of IIT Roorkee. Today I am going to talk about medical imaging techniques. I will talk about different modalities used for medical imaging and I will focus on the instrumentation part of these modalities. So following are the contents which I will be talking about. First I will talk about projection radiography. Then I will cover computed tomography, popularly known as CT. Then I will talk about nuclear medicine imaging, then ultrasound imaging, and finally I will cover magnetic resonance imaging, popularly known as MRI. So for understanding each modality, we need to first cover physics, then we need to cover its instrumentation part, then image formation, then image processing, and finally the image analysis. As this course focuses on instrumentation, so I will talk about the instrumentation part of each modality. Our first modality is projection radiography. So what basically projection radiography is? So projection is basically collapsing the dimensions. So in our case, we are going to talk about 3D volume that is collapsed and is projected to a 2D plane. So this is the reason it is known as a projection radiography. So the instrumentation of projection radiography consists of the following components: X-ray tube configuration, filtration and restriction of X-ray photons, compensation filters and grids, and film screen detectors. So in this general sketch, we can see all of these components together. They form the instrumentation of projection radiography. So our first main component is X-ray tube. So X-ray tube is nothing but it is basically a source of generating X-rays. So X-ray tubes emit electrons from cathode, which are accelerated by a high voltage towards an anode. When electrons strike anode, X-rays are produced through rapid deacceleration. So now coming over to the filtration and restriction part. So filtration and restriction of X-rays are done to minimize the X-ray dose given to the patient. Filtration is the process of absorbing low energy X-ray photons before they enter the patient. Restriction is the process of absorbing X-rays outside a certain field of view. Filtration can be done by introducing a few millimeter thick sheet of aluminium or copper. And on the other hand, restriction of X-rays can be done by introducing a small device known as collimator beam restrictor. You can see that device in the diagram on the screen. Now coming over to the compensation filters and grades. X-ray projection radiography relies on the principle of attenuation, where X-rays passing through a material are absorbed or scattered based on the material's composition and density. The intensity of X-ray beam decreases exponentially as it traverses through the material, following the equation I is equals to I naught e raised to the power minus mu delta x. Here in this equation, mu is linear attenuation coefficient and delta x is tissue thickness. Compensation filters are crucial in X-ray imaging to minimize the effect of variations in tissue thickness, that is delta x, across the patient's body. This can be clearly seen in the diagram on the screen. Now coming over to the grids. So what grids are doing is that they are decreasing the effect of Compton scattering. So when X-rays are passed through the human body, there are some Compton scattering happening there. This Compton scattering is basically the enemy of image quality. So for reducing the effect of Compton scattering, what we do is that we arrange some lens strips in such a way that it allows only the X-rays which are traveling in the straight line path. So any X-ray which is coming after the Compton scattering will be absorbed by these lens strips, and only the straight line traveling X-rays will be allowed to fall on the film. Now coming over to the most important part of instrumentation, that is film screen detector. So the film screen detector consists of two essential parts, the film itself and the screen. The film is typically crafted from light sensitive materials like silver halide crystals, while the screen contains phosphor crystals. So as X-rays penetrate the patient's body, they undergo attenuation, interacting with tissues and structures along the way. The attenuated X-rays then reach the film screen detector. When these X-rays hit the phosphor crystals in the screen, they emit light, exposing the film and creating what we call as a latent image. This process is key to forming the X-ray image we interpret. The intensity of light emitted correlates with the degree of X-ray attenuation in the patient's body. Thus, areas with higher attenuation appear darker on the film, while those with lower attenuation appear lighter. Now finally talking about optical sensor component in image intensifier. The optical sensor component comprising the fluorescent screen and photodetector plays a crucial role in converting emitted visible light into electrical signals. These signals are then amplified and processed for real-time display, facilitating visualization of dynamic changes within the patient's body. Now coming over to our next modality, that is computed tomography, popularly known as CT. So computed tomography is a technology that offers detailed cross-sectional images of the body with remarkable clarity and precision. Unlike conventional X-ray techniques, CT provides a three-dimensional view, allowing clinicians to visualize internal structures with great detail. The instrumentation of computed tomography basically contains the similar components as we discussed in projection radiography. So for the instrumentation part, first we will discuss about computed tomography generations. Then I will cover X-ray source and collimation part, which is different from that of projection radiography. And finally, I will be covering CT detectors. So first talking about CT generations. CT scanners measure X-ray attenuation along a line between a source and a detector to reconstruct 2D cross-sectional images. 7 generations of CT designs have been developed, each aiming to improve performances, especially in acquiring data faster. While the earliest generations are obsolete in medical imaging, understanding their geometry, like the parallel ray geometry of first generation scanners, is crucial for grasping reconstruction principles. Now I will cover each of the 7 generations quickly one by one. First, we have first generation introduced in 1970s. These scanners rotated a single X-ray tube and detector around the patient, capturing images slice by slice. Moving on to the second generation, which improved speed by using multiple detectors. This reduced scan times and enhanced image quality. Next, the third generation brought a pivotal change with the introduction of fan beam design. It allowed for faster scanning and reduced radiation exposure. The fourth generation further enhanced speed and resolution by using a rotating X-ray tube and stationary ring of detectors. Then came the fifth generation, introducing helical or spiral scanning. This continuous motion allowed for quick scans and improved image reconstruction. In the sixth generation, we saw the integration of multi-slice technology, enabling the acquisition of multiple slices in a single rotation. Finally, the seventh generation, characterized by iterative reconstruction techniques and advanced software aimed at reducing radiation dose while maintaining image quality. Now talking about X-ray source and collimation, most scanners use only one X-ray tube due to initial and maintenance cost. Collimation shapes the X-ray beam in CT scanners using lead collimators to target specific areas and minimize exposure to surrounding tissues. CT scanners employ a fan-shaped beams geometry, enabling precise imaging of cross-sectional slices. Lead collimators in CT scanners allow for adjustable beam width, optimizing image quality and reducing radiation exposure. Filtration selectively absorbs low energy X-rays in CT scanning, enhancing image quality and minimizing patient radiation dose, similar to projection radiography. Now coming over to the CT detectors. Modern CT detectors utilize solid-state detectors, which consists of scintillation crystals such as cadmium tungstate, or sodium iodide. When X-rays interact with this crystal, they generate photoelectrons, which emit visible light as they de-excite, similar to how a phosphor in a screen works. This burst of light is then converted into electrical current by a solid-state photodiode closely connected to scintillator. In some advanced scanners, photomultiplier tubes are also used instead of photodiodes for this conversion process. This can be seen in the following diagram. So the next imaging modality is nuclear medicine imaging. Till now, whatever I have covered, that is projection radiography and computed tomography, they are structural imaging and provide only anatomical image of bones and tissues. Nuclear medicine imaging is a technique which provides functional image of the organs. This type of imaging can be done in 3 ways, and hence we have 3 different modalities. I will cover each of them. So the first one is planar scintigraphy. It is basically a non-invasive imaging technique in which a radioactive tracer is sent inside patient's body. The gamma ray photons emitted by the tracer are then passed through a collimator to reduce Compton scattering effect. Finally, the photons are made to fall on a scintillation detector. This detector consists of a scintillation crystal which converts the X-ray photons to light photons, and a photomultiplier tube, which basically is a type of optical sensor that converts light photons into electrical signals. The second one is SPECT. SPECT is basically single photon emission computed tomography. The basic principle of imaging is similar to that of planar scintigraphy, except the fact that it uses rotating angle camera to detect photons so that 3D cross-sectional views of the organs can be obtained. Rest of the components of instrumentation are same as planar scintigraphy. The third and the last one is PET. PET is basically positron emission tomography. It basically detects paired gamma rays produced by positron annihilation using annihilation coincidence detection, known as ACD, as can be seen in the topmost diagram. It determines the direction of gamma rays travel without collimation as it uses ACD for detection. PET systems consist of multiple rings of detectors electronically coupled for efficient detection. The detectors work on the same principle as that of planar scintigraphy, utilizing a scintillation crystal and optical sensor such as PMT. The only difference is in the structure of the detector, as can be seen from the bottom two diagrams. The next modality is ultrasound imaging. Ultrasound imaging is also a non-invasive imaging which uses ultrasound, that is sounds which have frequency higher than 20,000 Hz. Its instrumentation consists of two major components which are the transducers and the probes. The complete circuit diagram of ultrasound system is shown in the diagram. Now coming over to the transducers and probes used in ultrasound imaging. So as we know, transducer is a device that converts one form of energy to other form. In case of ultrasound imaging, piezoelectric crystal acts as a transducer. It basically generates acoustic ultrasound pulses that bounce off internal structures and return to it. These returning waves are converted into electrical signals by this piezoelectric crystal. Then these are processed and displayed as ultrasound images. An ultrasound probe looks like a stick with a crystal at the end. This crystal sends out sound waves into the body and listens for their echoes. Basically, the type and quality of image as viewed by ultrasound imaging depends on the shape and size of the probe. Different types of probes are used to obtain different types of view according to the necessity. Now coming over to our last imaging technique, that is magnetic resonance imaging, popularly known as MRI. So the instrumentation of MRI consists of the following components. First, there is a magnet, then there are gradient coils, then radio frequency coils, and finally there are inductive sensors. So now talking about the principle on which MRI works. So MRI works on the principle of nuclear magnetic resonance. MRI utilizes powerful magnets to align the hydrogen nuclei in the body, then applies radio waves to temporarily disrupt this alignment. As the nuclei return to their aligned state, they emit signals that are detected by the MRI machine. By analyzing these signals, detailed images of the body's internal structures are generated, aiding in diagnosis without using harmful radiation. Now coming back to the instrumentation part, MRI contains following main components. The first one is the main magnet. It generates a strong and uniform magnetic field aligning hydrogen atoms inside the body. Second one is gradient coils. So they create spatial variations in the magnetic field. The third ones are RF coils, also known as radio frequency coils. They transmit pulses into the body and receive resulting signals. Now finally discussing about the role of inductive sensors in MRI. So as we all know that inductive sensors work on the principle of electromagnetic induction. They detect changes in magnetic field by converting them into electrical signals. Inductive sensors are utilized in various components of MRI machine. These are employed within the main magnet to monitor and control the strength and stability of the magnetic field. These sensors detect changes in current flowing through the magnetic coils and provide feedback to maintain the desired magnetic field strength and homogeneity. Inductive sensors are also integrated into gradient coils to accurately control the gradient fields. Inductive sensors are also used in RF coils for tuning and matching purposes. These sensors monitor parameters such as coil impedance and resonance frequency to optimize RF transmission and reception efficiency. These are the references which I took to prepare the slides, and that's it. Thank you.